Welcome back. So remember last time we had proven the Castelline theorem. Which basically says that planar graphs are Pfaffian. So if G is planar, if you fix omega an orientation such that, so we'll just call it a counterclockwise odd orientation, then the Dimer partition function is given by the Pfaffian of the corresponding skew adjacency matrix with absolute values. So I had proven this theorem, and I think I had just given a kind of a stupid didactic example. So I want to make a remark and then treat a really not stupid example. So the first remark that I should have made last time already, but you probably guessed it, is that if the graph is bipartite, then it has an even simpler form. So assume G is bipartite, and number the vertices with numbering first all the white vertices and all the black ones, or vice versa, we don't care. So let's say something like that, W1, Wn, B1, Bn. Then this matrix has the following form. It has this form where K is the corresponding bi-adjacency matrix. The corresponding. So it would be, it's a weighted, signed bi-adjacency matrix. And then, so the general Castelline theorem that works even if the graph is not bipartite in general case says that Z is the absolute value of the Pfaffian of this matrix. But so then it means it's the absolute value of the Pfaffian of a matrix of this form. And we saw it was one of the properties, number 4, of Pfaffians that I had talked about last week at the very beginning of the class. This is the same up to a sign as the determinant of K. So what do you get? In the bipartite case, we simply have that the partition function is given by the determinant of a signed bi-adjacency matrix. And you have some examples in homework. Right? Okay, now let's come to a really, really nice example. And I'm not going to do the details, it's going to be an exercise, so details are in exercise 1, homework number 5, the one that is here now. And it's a very famous example, so let G Mn denote the m by n square lattice with weights. So we're simply going to set some weight, let's say x, on the horizontal edges and some weight y on the vertical edges. Okay. So it depends on two variables. And we want to compute the Dimer partition function. So note that the number of vertices of this graph is equal to m times n. So if both m and n are odd, then the number of vertices is odd, so there is nothing to say, okay? It's odd, so there is no perfect matching and the partition function is 0. So we can assume without loss of generality that one of them, say n, is even, okay? Without loss of generality, let's assume that n is even. So then what you can do is simply you find a Castellan orientation on such a graph. It exists, okay? And then you try to make it kind of symmetric. That's one of the points of the exercise. And with this orientation being sufficiently symmetric, you have a matrix that is very symmetric. And so then you can express it as a tensor product, and then you can diagonalize the basic pieces, and then you have a very beautiful formula, which I'm going to write now. Using Castellan theorem, and it's interesting to see that actually, so this graph is going to be bipartite, but in this case, it's actually easier to compute the Pfaffian of the full matrix than to compute the determinant here. So it's funny, it's not a good idea here to pass through this remark here. But anyway, everything is explained in the exercise. One computes. So here's the formula. So I'm going to write it here. So I will write like this. It depends on two variables, x, y. So it is the product two. I will just double check that I didn't mess up the indices, but I think that's correct. That's right. I'm not claiming it's a trivial exercise, but you will all be able to do it with the indications. So I think this is absolutely unbelievable. So you have a closed formula in this form for the Dimer partition function for the square lattice with weights x and y like this. In particular, if you just, so let's, remember we started the class by asking questions about combinatorics and can you count the number of perfect matchings on the graph? And remember in the introduction I also told you, well, on the square lattice, counting perfect matchings is the same as counting domino tilings, you know? So now, in particular, setting x equal y equal 1, in particular, setting x equal y equal 1, what do we get? We get that the number of perfect matchings on an n times n lattice, square lattice, which is also equal to the number of domino tilings on the corresponding board, is equal to, so this same formula, so I'm going to give you some values in particular. For an n times n board, we have, so we have 2. So let's just put it this way. So I'm going to set n. So I want, of course, n to be even, right? If it's odd, we have 0. So you have 2, 4, 6, 8. And here are the number of perfect matchings or of domino tilings. So we have 2 here. Okay, this is, again, a stupid example, a 2 by 2 square lattice. So you have a square, how many tilings? That's fine. So it's like a reality check. Then 36 on a 4 by 4. That's already not so obvious. Then 6,728, 6 by 6. Then 12,988,816 domino tilings on an 8 by 8 board. So in this case, it's not only that you're able, if you really want, to compute things in the polynomial time, it's that you have really a closed formula. This is really, this I find a really amazing result. So it's due to Castelline. This is due to Castelline in 61. And remember, I had asked in the introduction, well, how does the number grow? Remember, I had asked what is the growth of this thing. So also, one can compute what is called the free energy of the model. Here, I'm just going to write it as, so the limit as n goes to infinity of 1 over n squared, so that's the number of vertices of the graph. It's the log of the number of perfect matchings. So it means the number of perfect matching grows as exponential of n squared times a number. And this number then can be computed using this formula. You can actually compute the number. I'm not going to do it here, neither in homework, because we're actually going to see a much more general result in maybe 3 weeks, well, after the holidays. But this number here can be computed. It was done by Castelline, and this is equal to g over pi, where g is Catalan's constant. And this number gives you roughly and you remember 2 weeks ago, we had seen that there were some bounds on this number, upper and lower bounds, because it's a 4 regular graph, well, if we put it on a torus, and we had seen some upper and lower. Now we have the exact value. It's possible to compute the exact value, and that's it. Okay. So we're not, again, no detail here, because actually it's the most amazing thing. We're going to see in the next chapter that, so in general, having this kind of closed formula is not, well, it's a little bit difficult. Well, we will have them as a determinant, but of course, if the graph is not that symmetric, you cannot expect to have this kind of formula. But on the other hand, if you want computing the free energy, actually, you will have a closed formula all the time. Well, it's written as a double integral. We're going to see this. But so actually, if you have a bipartite graph that is on the torus, then you have a huge technology that allows you to compute this kind of things. So no detail here, because we will see something much more general. See next chapter for a much more general, for very general setting. Maybe a couple of remarks before going on with consequences of the Castellan theorem. First remark is that, so Castellan theorem says that planar graphs are Pfaffians, okay? So Castellan theorem says that G planar implies G Pfaffian. So it is not true that all Pfaffian graphs are planar. So, but that's the remark. But there are Pfaffian graphs which are not planar. And this was also an exercise 4, homework 4. The second remark, so now what we're able to do is count perfect matchings on planar graphs. This we can do in an efficient way. So we could ask, well, okay, now let's try to count all matchings on a planar graph. And this is a Sharp-P complete problem. So if you remember at some point I told you the perfect matching stuff is at the exact right level of difficulty. It means we're able to do it. But if you just twist it a little bit, it just all breaks down. So if you're not looking at planar graphs, that's Welian theorem, it's hopeless. And now if you don't look at perfect matchings, but you look at all matchings, you can also not count this. So counting the number of not necessarily perfect matchings, also known as Dimer monomer configurations. Let's just say Dimer, yeah, okay, coverings. Is actually Sharp-P complete. And I forgot who proved this. It's a theorem from the 70s, but I forgot who proved it. Yes, Daniel?
That the matching is maximal under infusion or not?
So I'm sorry. Now that you ask a question, I'm just I should here add that here it's on, I think I said it, but I didn't write it. It's on planar graphs. And I'm going to answer your question straight away. So we knew already that even counting perfect matchings on an arbitrary graph was sharply complete. But now, even if you restrict on planar graphs, where we know we can count efficiently perfect matchings, if you count not necessarily perfect matching on planar graphs, then this is sharply complete. And I'm not assuming that these are maximal matchings, just any matchings. Okay? Counting the number of maximal matchings on a planar graph, I don't know if it's. I expect it's actually also sharply complete, but I don't know the answer. Okay, sorry, I had forgotten this. I hope now it's clear. Okay, so I hope you get a sense of how these problems are really, it's quite subtle. So if you really look at the right thing, you can count them, you can have nice formulas, but if you just go a little bit aside, it just breaks down, you're not able to do anything. Okay, so a further consequence of Castellan theorem we can express so-called edge-edge correlations. So let me define this. I think I didn't do it so far. For those who were at the seminar yesterday, the speaker said at some point, he said, we're not using Castellan theorem. People using Castellan theorem, then they compute edge correlations, and he said something like, so this is exactly what I'm going to explain now. So let E1 EK be edges of the graph, edges of a planar graph. Well, okay, let's just start with the abstract setting of a weighted graph. The edge correlations are by definition, so they are denoted this way, E1 EK. And by definition, this is simply the probability that a given matching contains all these edges. And we'll see later on that, well, you can guess, but we'll see later on that these are important quantities for the model. And so now I claim that with Castellan theorem and with the properties of Pfaffians that we know, we can actually express this in a very simple way with the Castellan matrices. So let's see this. So now assume that G is planar, or let's say planar. Let omega be a Castellan orientation. And set, I'm going to write A for the corresponding Castellan matrix. And I'm also going to set I for this set of vertices. Okay, now it's going to be a one-line computation. So then, what do we have? So I want to, so again, remember this is, by definition, this is simply the this probability. So how can I write this? So I can write this as 1 over the partition function times the sum over all matchings that contain these edges of the weight of the corresponding matching, that is product right? This is really by definition of the measure. Or okay, so it means that now I can factor out all the weights of these edges. So what do I get? Get nu E1 nu EK over Z times. And what do I get here? I claim that here I get the derivative of the partition function with respect to these weights. Okay, you just consider these weights are formal variables and you make the kth partial derivative of z with respect to this, right? I think that's clear. Okay, but what is good now is that, well, we use Castelline. So Castelline theorem. So we have nu E1 nu EK over the Pfaffian. So maybe I'm going to put an overall sign here. I'm not going to be precise about the sign. And here you have Pfaffian of A. And here you have the derivative of the Pfaffian over. So here, remember, the coefficients of the matrix corresponding to the vertex I1, J1 is exactly this weight up to a sign. So I just put all the signs outside, and here I have the A1, J1, IK, JK. Okay, but now we're happy because you remember we had one property of the Pfaffian that was exactly expressing this thing here. And you remember there was a first property, it was property 5, I think. It was expressing this as something times, well, there was a factor Pfaffian, and then, well, okay, so these are properties, I'm going to use the numbering, it was 5 and 6. And here I use, so property 5 was true in full generality, and property 6 was true if the matrix A was invertible. But we of course know that the matrix A is invertible. Why? Because its Pfaffian is equal to a partition function which is non-zero. So okay, we assume that there is a perfect matching. Okay. So here we use the fact that the Pfaffian of A is equal to Z, which is non-zero. So the matrix A is invertible and we can apply everything. So and what do we get? I get, again, a sign times the Pfaffian of A inverse I. Where you remember, this means you take the inverse matrix and you just focus on the lines and columns that are in this set here. Okay. So we proved and I don't know to whom this theorem should be attributed. Castelline, I don't think Castelline ever wrote this down. I think Kenyon, Rick Kenyon is the first one who made this observation, but I'm not completely sure. Let G be a planar weighted graph. And let A be an associated Castellane matrix. Then, for any edges U1 EK as above, we have is equal to the product of the weights times the absolute value of this, where denotes the I rows and columns of A inverse. Maybe just one example. Let's consider the case k equals 1. So what do we get? K equals 1 if we have one edge corresponding to the vertices ij. Then the probability that perfect matching contains this edge is given by what? So we have the weight of this edge times the absolute value of the Pfaffian. And now we're going to have a 2x2 matrix, right? Only with lines and column ij. And so this will be 0, A inverse ij, A inverse ji, which is minus A inverse ij, 0. The Pfaffian of a 2x2 matrix is, well, it's this coefficient. So we simply get nu of E times the absolute value of the ij coefficient in the inverse Castellane matrix. Okay, and if so, maybe see homework 5 for more concrete examples. Okay. And maybe just as a remark, again, in the bipartite case, you have a simpler formula, or let's say you can express everything only with the bi-adjacency matrix. So once again, in the bipartite case, we have a simpler formula. And it's the following one, and it's a one-line exercise to check it. So if A omega is, again, the same notation, then, so, and let's say that the edges are of this form, EK, WK, BK. Then the edge-edge correlations are given by, so of course the same product times the absolute value of the determinant of the matrix K inverse Wi Bj So I'm changing a little bit the notations, but I hope it's clear. So it means, well, it's exactly the same statement, but you look at the, well, you change the Pfaffian with the determinant, and you look at the bi-adjacency matrix and not the full adjacency matrix. And again, it's a one-line argument, so I'm not giving it. It's immediate. Okay. So now comes the question of how to extend Castelline theorem. So question. How to extend Castelline theorem to graphs that are not planar. So of course we know that it's not going to be given by a single Pfaffian. This is not possible because of a Valiant theorem. But is it still possible to say something? And Castelline himself, he had ideas about this. So in his articles in the 60s, he made two observations. First, he said that he actually gave a formula for the square lattice embedded in the torus. And he showed that for the square lattice embedded in the torus, you have, you will need to have 4 different Pfaffians and to sum them up in the right way. And then he stated without proof that in general, if you have a graph that is embedded in a surface of genus G, then you will need 4 to the power G different Pfaffians. That's what he stated. Then there was no proof. And okay, then it's a long story. There were several people who attempted some proofs. Some were not so bad. But the problem, so i.e. when G is embedded in a surface of genus G. Let's say a closed surface of genus G. So the issue here is we used planarity in Castelline theorem in a very crucial way at some point in the proof, you remember. So as I said already last time, if you just want the Castelline condition counterclockwise, oh, this makes sense on an orientable surface. So here, of course, it's an orientable surface. Let's even say oriented. So it makes sense to talk about counterclockwise. So you orient your surface, and then you say, okay, I want all my faces to have this Castelline condition. So this makes sense. So you can have, so the first lemma works. Then the second lemma, remember, we're saying, okay, you have a cycle in the plane. So a cycle in the plane bounds a collection of faces, and then we started an induction, right? And here, of course, this is not true in general. If you have a cycle on a surface, it might bound or it might not bound. Okay. I just wonder how much I should say before starting the actual topic, but it's an interesting thing because then you might think, okay, but I'm going to try to work it out just by brute force, combinatorial brute force. So I have all these cycles on the surface, and I will try to compute things, and it's going to work. So this is let's say this is possible. One can work out a proof, but it's extremely annoying because You see, will just have arbitrary configurations of cycles on the surface, and you need to try to count the Dimer configurations, things, and this is very, very tedious. So what I would like to present to you now, it's going to be it's a proof, it's an extension of Castellan theorem that uses some geometrical tools and where you have strictly no combinatorics to do. It just flows very easily. So the problem is, of course, that it will use these tools, and I need to explain these tools to you now. And so this is what I'm going to do. It's the paragraph 2.3, and it is, I denoted a crash course on, so there are 3 tools, so to speak, homology, quadratic forms, and spin structures on surfaces. And it's too bad because basically I'm only going to be able to go halfway through and then there will be the holidays. But okay, let's do it. So, so again, so in Castellan's proof, we used the fact that a cycle in the plane bounds a collection of faces. This is not true anymore for surfaces. This is not true if the graph is embedded in a surface of genus higher than 0. So, right, you take a torus, and you look at a cycle like this. It doesn't bound. However, there is a tool that exactly measures the defect of cycle versus boundaries. The defect of, it measures how many cycles do not bound. So, however, there is a tool which measures the defect of cycles versus boundary. And this is called homology. So this is the first part. So it's going to be 3 small paragraphs, one on homology, one on quadratic forms, one on spin structures. And each time, obviously, I'm going to focus each time it's, let's say, big theories. And each time I'm going to focus on specifically what we will need. But I'm not going to prove anything. So I will, for those interested, I can give references for proofs of all these things. But okay, I will not give any proofs. Okay, maybe we make the break now. We resume in 15 minutes. Let me just go back a little bit. I should have made a remark. So here, I was using these properties of the Pfaffian, and I should have said, so here I will, for these formulas to hold, I assume that all these edges are disjoint, right? If the edges, I mean, it holds to some extent if the edges, so if the edges are not disjoint, then obviously this is 0. You never have a matching, okay? On the other hand, it's just that this doesn't really make sense. So I was using this notation I for I1, J1, IK, JK. And I should have said that these indices are assumed to be distinct, okay? Let's say with distinct indices. Then the formula holds. And if they are not distinct, then it's easy to see that this partial derivative of the Pfaffian will always be 0. So it still makes, I mean, the computation still makes sense. You just have to understand that if these indices are not disjoint, then this is 0. That's it. Okay, good. So now let me go back to homology, which is a topological theory. Okay. So again, it's going to be only the parts of the theory that are needed for our purposes, and no proof. And again, if you want references, I'm happy to give some to you. Okay, since we're dealing only with surfaces, I'm going to assume that my topological space is a surface. So let sigma G be a closed orientable surface. Okay, so of genus G. Okay, so you know what this looks like, I guess. This is a genus 3 surface. And let G be embedded in the surface and will so be graph embedded in sigma. And we're going to assume one thing is that such that the complement of G consists of topological disks. Okay. That we call faces. Okay, so this simply means that I want the graph to approximate my surface sufficiently well. Okay, so for example, a counterexample would be you don't want something like I don't know, let's say something like that, for example. So this will actually mean that you encode the topology of the surface in a sufficiently good way with your graph. Okay. So now we know what are the vertices, we know what are the edges, we know what are the faces. So let C0 denote the Z2, so respectively C1, C2, denote the Z2 vector space. We're going to form a vector space over Z2 with bases the set of vertices, respectively of edges and of faces of gene sigma. Okay, so this means C0, it's just linear combinations of vertices. And linear combinations counted modulo 2. So it's this vertex, not this one, not this one, etc. Just make a sum. And same thing for C1 with edges and C2 with faces. Okay? So these are finite dimensional Z2 vector spaces. Okay, so the graph is finite. I mean, we look at only compact stuff. Okay, now so define boundary operators as follows: 0, C2, D2, we'll write D3, C1, V1, C0, E0 like this. Each time you want these to be linear maps, and you want them to define a boundary. So I'm just going to say in the obvious way, and I'm going to make drawings in the obvious way. That is, so I only need to define delta 2 and delta 1. The other ones are trivial. So let's see, how can I define delta 2 of a face? I have a face F. It's a topological disk. So you have some kind of boundary made of edges. And you will simply, and you want this to lie in C1, that is sum of edges. You do the obvious thing. You just define this as the sum over all edges in the boundary of F. Okay, and this does lie in C1, right? And this is the way you define the boundary on a face, and then you extend this linearly, okay? You understand this definition?
Is there some orientation?
Yeah, so that's a very good question. So the point here is that we work over Z2, and over Z2 you don't need orientations. So it's part of a very general theory where in general you can work over Z, or actually over any abelian group, and well, let's say any ring. And then if you work in something that is not of characteristic 2, then you will need orientation. Then things get, just the definitions here get much more tricky. But here it's miraculously simple. It's you just sum everything. You don't care about signs because you don't care about orientations because you don't care about signs because you're working modulo 2. Okay. And then I need to define the one boundary, so delta 1 of an edge. So if I have an edge E vertices V1, V2, I of course define this as V1 plus V2. And this lies in C0, and again, I extend it linearly. Okay? Now let me just draw a couple of examples. What is delta 1 of a path? You see, I have this path made of edges, and I want to compute the boundary of this path. So it is delta 1. So since I extended, delta 1 is linear. So this is delta 1 of this plus delta 1 of the second one plus etc. Okay, let's say E1, E2. Daniela, do you have a question? Good. So this was a kind of a way to tell you, please, to stay quiet. Thank you. Yes? Yeah.
About the first definition, so if there's a leaf edge picking into the face, do we count it twice?
Yes, that's also a good question. Indeed, you count it twice. So if you, so maybe I'll just, this could happen, and in this case, indeed, this edge will be counted twice. So this will be equal to this. Okay. That's right. So coming back to this example, you see, I'm gonna. So now this will be maybe. Let me just write V2, V3, Vn. What I will have at the end of the day is V1 plus V2 plus V2 plus V3, but we're counting things modulo 2. So all these vertices that are in the middle, they're going to be counted twice, so they are 0, and so you end up with only V1 plus Vn. And this is obviously what we would like geometrically to have as the boundary of this thing. And this is now, you see, if you have oriented stuff, this is where it gets a little bit tricky. Well, here it's still okay, but then we need to orient your edges and to count the boundary of this edge as V2 minus V1, and then it works. You see, we'll have a telescopic sum. In dimension 1 is still okay, but dimension 2 or higher, it gets really messy with the orientations. So here we're happy we don't have to deal with this. Okay, so this was this, and then another example, delta 1 of this, that is delta 1 of a cycle. What do you get? Well, you'll get 0, right? And this will motivate the definition, the kernel of delta 1, that is the collection of edges such that their boundary is 0, you will call these cycles. Okay. 1 cycles. Okay. Let's make another example. Delta 2 of, I want this face plus this face. Now I guess you get the picture. We'll sum all the edges, but the edge that is here in the middle, it's going to be counted twice. So what we get here is something like that, which is indeed what you want to have as the boundary of this family of faces. Okay. And again, if you think about it, then if you want signs, if you want orientations, then it's a little bit more messy. You need to orient the faces. And if you orient them in a coherent way, then indeed you will have this edge that's going to be counted in the other orientation than this one, and then it also cancels out. But here we're counting module 2, so we don't have to deal with these stuff. Okay. Good. And so now let's... Now note that, okay, maybe I'm just going to make one last example, is that I'm just going to say that when you make, so this element here, it is, we were going to call this a boundary, because it is obtained as the boundary of a collection of faces. Okay, so I'm going to say that the image of delta 2 is going to be called 1 boundaries. It's the collection of 1 boundaries. So you see, this is precisely the formalization of what is a cycle and what is a boundary. What does it mean to bound faces? It's being a boundary. It means you're in the image of delta 2. What does it mean to be a cycle? It means when you take the boundary, you get 0. Okay? And now, note that if you take the delta 1 of delta 2 of a face, what do we get? So this is delta 1 of the sum of edges that are in the boundary. And this is 0. Right? And it works for a face, but since we extend everything linearly, it means that if you do delta 1 composed with delta 2, it's always 0. This is equivalent to saying that the image of delta 2 is included in the kernel of delta 1. And by definition, this means that boundaries are cycles. 1 boundaries are 1 cycles. Right? If you bound a collection of faces, then you are a cycle. And of course, trivially, we have all the other composition, delta k composed with delta k plus 1 is always 0 for any k. Because if you look at the others, they always, you always have a trivial map among these two. Okay, remember we had so if you compose two, you always have 0 trivially, except in this case where we just saw it. Okay, and therefore it means that the image of delta k plus 1 is always included in the kernel of delta k. Okay? And therefore hence one can define so hk of sigma with Z2 coefficients is defined as the quotient of the kernel of delta k by the image of delta k plus 1 is the kth homology group of sigma with Z2 coefficients. So it's actually a Z2 vector space Okay, so now I'm going to give you some facts. So fact A1, which is the most difficult one to prove, is that, well, here you guess it because I didn't write hk of g, I wrote hk of sigma. So this thing here actually does not depend on the graph we started with in the surface. So hk sigma z2 does not depend on g in sigma. Technically, we speak of g in sigma as a cellular decomposition of the surface. Okay? It does not depend on the way you have approximated your surface in a combinatorial way. So it is a topological invariant. I'm just going to say here that this is kind of hard. This is a hard thing. I mean, maybe for surfaces it's possible to give an elementary proof, but this, again, is part of a big theory where you actually work with very general topological spaces, and this always holds. And I don't know of any elementary proof even in the case of the surface. Okay. But, okay, so for two of them it's easy. So K, here the interesting cases are K equals 0, 1, and 2. Okay? Otherwise, you have zeros everywhere. So let's be a little bit more precise. So more precisely, what is H0 sigma Z2? I should have said from the beginning that I assume my surface to be connected. I guess it was included in the fact it's of genus G. And actually, that's going to be an exercise in homework 5. It's very funny to try to unravel the definition of this and to see that actually this measures the connectivity of the surface. So this is actually Z2 because sigma is connected. More precisely, if you look at H0, it says, okay, whenever you have a cycle, does it bound? So it means whenever you have, well, any collection of vertices is going to be a cycle because everybody is mapped to 0. So whenever you have a collection of vertices, does it bound? Well, the point is if you have one vertex, it will not bound. If you have two vertices, since the surface is connected, you will find a path between both. It means you have a collection of edges whose boundary is going to be these two vertices. And therefore, this is equal to Z2, because it's not 0, because you have the cases of odd number of vertices. So this is an exercise. Homework 5. This is easy. Second easy part, H2, sigma Z2, is actually also of dimension 1, Z2, and this is because sigma is closed. So what is this? Again, it's a funny exercise. You unravel the definition. It means you look at the kernel of delta 2. Then you quotient by nothing because you have no delta 3 here. Okay? So kernel of delta 2 means you need a collection of faces whose boundary is 0. Again, if you think about it, when you have a collection of faces, it's always going to bound. But if you actually put all the faces of your surface, you just make the sum of all the faces. Since the surface is closed, it has no boundary, this is actually going to be a cycle, and it's the only one because the surface is connected. So it is closed and connected. That's homework number 5 as well. So actually, H0 and H2 in the case of surface, it's very easy to understand what is the geometrical meaning. And now H1 is really the thing we're interested in. H1 sigma Z2. By definition, this is the 1 cycles quotiented by the 1 boundaries. It means this vector space exactly measures the defect, what I was talking about before, the defect of cycles being boundaries. So I'm not going to write it again. It measures the defect of cycles being boundaries. And that's the not easy part. This will be a vector space of dimension 2G. So where G is the genus. Again, it means if you have a graph that approximates well enough your surface, then when you compute this, it will not depend on your graph. It just depends on the topology of the surface, that is on the genus. This is what you get. And maybe let's just make some examples. So G equals 0. It means that H1 is equal to 0. And this is simply telling you the fact that on a sphere, whenever you have a cycle, it bounds. Okay? All cycles bound. Right? And then in the case G equal 1, this statement says that the first homology of the torus is going to be of dimension 2, and you can guess 2 natural generators of the homology. It would be this alpha and beta. These are 2 cycles that do not bound, and both of them are actually different. If you take their sum, it also does not bound. Okay? So basis of the homology is given by alpha beta. That's one example of basis. And then in general, you can imagine you have a genus G surface. You easily guess 2G independent cycles. Like that. Okay, that's the first fact that I needed. And I need a second fact of homology theory. So that's second fact, let's say A2. So I'm numbering the facts like that, A1, A2, A3 for the first part. The intersection form, the intersection of cycles, let's say modulo 2, give rise to a well-defined bilinear form, which of course we call the intersection form, on H1. That is, you have a form like that, and I will denote it this way with a dot here. What does this mean? It means if you take a homology class here, you're represented by a cycle. If you take another homology class, you're represented by a cycle. Now you can choose these two cycles to intersect transversally. You count the number of intersections of the cycle, and you count this, and it's going to be this number. This number is not going to depend on the way you chose your cycles in the homology classes. Okay? Example. Example. Let's take the case G equals 0. So in the planar case or spherical case. What does this mean? This is 0. This is 0. So a bilinear form will give you 0. So it means you take any two cycles in the plane, you make them intersect transversely, they will intersect an even number of times. Right? That's a well-known fact, but it's actually a topological fact in nature. So G equals 0, this exactly means two cycles in the plane intersect an even number of times. And again, if you want, you can work with z coefficients, and then you count, so you have oriented cycles, and you count the intersections with signs, and then it works. You have a form that is defined over z, but okay. That's the G equals 0 case. If you look at the G1 case, then you see that you can get cycles that intersect an odd number of times. Here you see that alpha section beta is 1. Okay, so I think this is something useful to have in mind, that actually when you're counting intersections like this, what you're really looking at are topological statements. You might think it's geometrical, but it's topological. Okay. I will give you a third fact. Not that you will need it, but it's very nice, so I want to give you this. Define the Euler characteristic of the surface by Euler characteristic of the surface is defined as the number of vertices of the graph. So you embed a graph, as I said at the beginning, and you count the number of vertices of the graph minus the number of edges of the graph plus the number of faces of the graph. And now, easy exercise. It's again in homework number 5. If you look at the number of vertices minus the number of edges plus the number of faces, Well, by definition, this is actually the dimension of C0. This is the dimension of C1. This is the dimension of C2, right? That's the way we defined these spaces. They had as bases the set of vertices, the set of edges, the set of faces. So this is the dimension of C0 minus the dimension of C1 plus the dimension of C2. And the easy exercise I'm talking about is here. Is that actually you use the rank theorem in linear algebra and you show that this is equal to the dimension of H0 minus the dimension of H1 plus the dimension of H2, which is equal by fact, the first fact, to 1 minus 2g plus 1, that is 2 minus 2g. And so you get that if you have a surface of genus G, you embed a graph in any way you want, such that the faces are topological disks, then if you count number of vertices minus number of edges plus number of faces, it's always going to be the same result. That's a topological invariant. So the exercise, as I phrased it in homework 5, is if you assume that the homology groups are topological invariants, prove that the Euler characteristic also is a topological invariant. And this is actually the birth of homology. So it's Poincaré who wanted to prove the Euler formula. So because you know that in the case G equals 0, this is the Euler formula for polyhedrons. For, let's say, convex polyhedron, means that if you have a convex polyhedron, if you take the number of vertices minus number of edges plus number of faces, you get 2, right? And Poincaré was interested in this, and he had the idea to use linear algebra here to solve this problem. And when you were counting these dimensions, you're really counting, in the old times, they were really looking at big set of equations and counting the number of solutions of these equations. And that's the way Poincaré came up with homology. Okay. So unfortunately, I need one more fact that is not so funny. There is a dual theory that is called cohomology, and I'm just going to state how it's defined and not say too much about it. But we actually will use this, so I want to tell you just a little bit about it. So there is a dual theory called cohomology, which is defined as follows. You just take what is called a chain complex that we had, so C2, C1, C0. And just look at the dual. And apply, so I'm going to write it this way, and apply hom to Z2. So it means, so if you writing CK for hom CK Z2 and delta K for delta K star, the dual, we get something of the following form. So we get 0, C0, C1, C2, 0, and the deltas, so I have to check. So that's delta 0, delta 1, delta 2, delta 3, with each time you compose delta K composed with delta K minus 1, this is always 0. And therefore, one can define H with a K on top, sigma Z2, which is equal by definition, so it's the kernel. So I have to focus a little bit. This is kernel of delta K plus 1 over the image of delta K. And it's called the kth cohomology group. Of sigma. Again, of course, it's a Z2 vector space. And, okay. So I'm saying it's not that funny because it is less geometrical. You see, the homology is totally geometrical. You understand everything that's going on here. It's more, you see these elements here, they are maps on sets of faces or vertices or edges. It's a little bit less intuitive, but okay. And the fact that I will need, so that's fact A4, no, 5. Yeah, okay, no, actually I already numbered it, so it's, sorry. So A4, so the fact that I will need is that these are also, so the fact is these are also topological invariants. And if you look at H upper 1, first cohomology group, actually it is isomorphic to the dual hom of H1 sigma, which I want to denote as like this. So it's also of that. So in particular, it is of dimension 2G. Okay. So that's the end of the crash course in homology. Don't worry too much about the last part. The homology, we'll use it a little bit, but it's not that important. But the homology, I would be happy if you have some intuition on this. This is going to be important. Okay, so now I will give you a very quick crash course on quadratic forms. So yeah, I will just start this, but this is easy. So this is really. This part is very easy, it's algebra. Doesn't mean that algebra is always easy, but in this case, it's really the case. Then the third part is going to be after holidays, and it will be about spin structures, and this is really geometry. Okay. So let H be a finite dimensional Z2 vector space endowed with an alternating bilinear form, which I will denote by the dot. So denoted like that. And alternating, if you don't know, this means that alpha with itself is 0 for any alpha. And of course, the case that we will keep in mind, that we should keep in mind, so for example, you take H, the homology of the surface, and the dot, the intersection form. Okay, definition. A quadratic form on H equipped with this form is a map Q H to Z2 such that, so If I write this, it means it's a linear map. Everybody knows what this is. So it is not a linear map, but the defect of linearity is measured by the quadratic, by the bilinear form for any alpha beta in H. Remark. If you look at Q of 0, this is Q of 0 plus 0. That is Q of 0 plus Q of 0 plus 0. And this is twice Q of 0. So this is 0. So quadratic form will always send 0 to 0, but then for all the other, let's say, basis elements, you have some freedom. So here again, I'm just going to list some properties of quadratic forms that frankly could be given and will probably be given as exercises. It's very easy. And then what we're going to do is, the next little chapter, we will focus on quadratic forms on surfaces. So it means quadratic forms defined on the homology of a surface. And it turns out that these are the algebraic avatar of a geometrical structure which is known as a spin structure. And there is one theorem, which I will state without proof, that links both. So it tells you, okay, if you have a spin structure, which I will define, it corresponds in a unique way to a quadratic form on the homology. So we'll have everything, we'll have kind of a black box that encompasses some very nice geometrical statement. And then, so that will probably take another hour. And then I will use this. It's going to take maybe 2 more hours, so not the week after holidays, but the next one, where we will use this again to show what we want to show, that is a general Pfaffian formula for a graph that is embedded in a surface. And if you put the case G equals 0, you get back the Castellan theorem, but in this case now we're going to have a formula that is valid for the general case of a surface of arbitrary genus. Okay? Enjoy the holidays. See you in 2 weeks.